Hi, everyone. Thank you so much for joining us for this last SURF webinar of 2023. Today, our webinar title is PFAS Remediation, How Will It Impact Greenhouse Gas Emissions? Next slide. My name is Gerlinde Wolf, President of the Sustainable Remediation Forum, or SURF. SURF is a non-for-profit professional organization comprised of members from all across the remediation industry. We are dedicated to advancing sustainable remedies and practices on a local and global scale through collaboration, education, and innovation. If you're new to our SURF webinar series, take a look at our SURF website, newly redesigned. There's a lot of great information there on the organization, a lot of good resources. You can also follow us on social media and sign up for our newsletter so that you can be notified for future events. Today we have a 2-for-1 webinar where 2 SURF members will share their recent work related to the environmental footprint impacts of PFAS remediation and treatment. First up, you'll hear from Ben McAlexander, who is a lead project geologist and hydrogeologist at Tri-Hydro. And then we'll hear from Paige Molson, an environmental engineer at Jacobs. Ben's half of the webinar will focus on the environmental footprint of treating PFAS from drinking water, one of the first priorities for many stakeholders involved at PFAS impacted sites, and something that you're likely currently encountering on your sites right now. Paige will then give us an overview of what we might see in the future when we sort of shift focus to treatment of PFAS on a larger scale for plumes or source areas. We welcome and encourage questions from the audience. Please enter your questions into the chat box on the right side of your screen, and we will have a question and answer session at the end of both presentations. Ben, please start us off.
Thank you, Gerlinde. As she just told us, we are first going to look at a very specific topic before Paige really broadens things. We are going to look at what kind of greenhouse gas emissions can we expect for PFAS treatment of drinking water by a specific technology, activated carbon. This is work that I did with Mitch Olson at Tri-Hydro and Honor Oppel and Jean McRae at the University of Maine. Currently, drinking water in our country is regulated by the states. Many states have promulgated standards per PFAS, and many others have draft or other pending standards. Most of those states regulate individual PFAS compounds. The state of Maine takes a sum of approach where you have to meet a certain total PFAS concentration target to have drinking water that meets the standard. Specifically, in the state of Maine, we have an interim drinking water standard of 0.02 micrograms per liter for the sum of the 6 PFAS shown on the right side of this slide. They include PFOA and PFOS, the 2 most studied PFAS, and 4 other PFAS that have similar chemical structures. That 0.02 microgram per liter standard is an interim one, and our state is on the hook to have a final maximum contaminant level by June 1st, 2024. So if we're starting to think about treating PFAS and the greenhouse gas emissions associated with it, this is a good place to look because the actual final cleanup level hasn't been established, and we can start looking at different possible cleanup levels and emissions associated with those. Some drinking water in our state before treatment is impacted by PFAS at concentrations that exceed the interim drinking water standard. That includes, in some cases, almost entire neighborhoods where private wells exceed the interim standard, and our Department of Environmental Protection is currently going to those homes. They've installed point of entry activated carbon treatment systems at those homes so that the PFAS can be swept out to meet that drinking water standard. That activated carbon technology is one of several ways that you can target PFAS and remove them from drinking water. It's also possible to use ion exchange or reverse osmosis, but of those technologies, activated carbon is the most established currently and is likely to be used the most in the near future. That the treatment achieved by activated carbon is strongly affected by your target PFAS concentration. The lower that target level, the higher the activated carbon quantity that will be needed to achieve the treatment that you desire. The reason for that is because activated carbon is a non-selective treatment media. PFAS sorb really well to activated carbon, and so do a lot of other things that are in water, such as dissolved organic carbon. So the lower your target level for PFAS, the more intense the competition for those adsorption sites gets, and then you need more and more activated carbon to get the treatment you want. Activated carbon can be sourced from coal. To do that, the coal has to be activated by steam to create a highly porous and absorptive structure. You can also get activated carbon sourced from biomass. A lot of people use coconut shells. That biomass first has to be carbonized in high heat and low oxygen, and then you take that carbonized material and activate it by steam. All of those processes to make activated carbon are energy intensive, and we emit a lot of greenhouse gases to the atmosphere when we make activated carbon. For instance, to make 1 kilogram of activated carbon sourced from coal, we emit about 18 kilograms of CO2 equivalent to the atmosphere. The emissions associated with making biomass-based activated carbon are lower, but they're still really high. Our team understood this, and we suspected that as we start treating drinking water on large scales to remove PFAS to low target levels, that might mean significant greenhouse gas emissions. But how significant? How big? So we went ahead and did some simulations of activated carbon treatment of PFAS contaminated drinking water. We simulated two different water supplies. One is a municipal water supply with a lot of users, and one is a residential water supply with just one household. We use starting PFAS concentrations that are based on data collected here in the state of Maine. You can see about 0.3 to about 0.4 micrograms per liter for the sum of 6 PFAS. And then we wanted to know if we take that raw water and treat it to the current drinking water standard here in Maine, what kind of greenhouse gas emissions can we expect? And then what if we treat to a less stringent standard, say a target concentration that is 2 times the standard, the current standard? What about 10 times? And then what about more stringent standards? What about a target concentration that is 0.5 times or 0.1 times the current standard? To do those sorts of simulations, you have to calculate for a starting raw water concentration, how much activated carbon will you need to treat to a target water concentration. And we were fortunate that adsorption parameters were available in a nice study that provided that data both for coal sourced activated carbon and for biomass sourced activated carbon. Once we calculated how much treatment media you need for each scenario, we then calculated emissions that included the following components: activated carbon production, building and shipping of the treatment vessels to the treatment site, shipping of the activated carbon from the vendor, and the most likely vendor for most of our treatment systems will be in Pennsylvania. Activated carbon disposal by thermal desorption. That's once you've finished with your treatment media. And then once you desorb the PFAS from your activated carbon, we did not include destruction of the PFAS. That's a really big topic, and there are a lot of different directions you could go with that. So to keep things simple, we did not include PFAS destruction. So we did our simulations and we came up with the graphs that you see on this slide here. On the left side of the slide, we have private residential water treatment, and on the right side, we have municipal water treatment. On the top set of graphs, we have coal-sourced activated carbon, and on the bottom, we have coconut-sourced activated carbon. Then on these axes here, these x-axes, we have the target PFAS water concentration. That includes 0.02 micrograms per liter. That's our current standard. And then if you go to the right of that, you have less stringent standards or higher target water concentrations. And if you go to the left of that, then you have more stringent standards. And then the y-axis on these graphs, the left y-axis is the total annual emissions that can be expected for a certain scenario. And then on the right side, the right graph or the right axis, we have the per user annual emissions. So it's a normalized value. So what we can see when we look at this is if we're just looking at coal source activated carbon at the current drinking water standard for our state of 0.02 micrograms per liter. Of course, we have lower emissions in the residential water treatment scenario than in the municipal water treatment scenario. These values on this y-axis are way higher than they are on this one. And that makes sense. On a total emissions basis, you're going to have a lot more greenhouse gases emitted to the atmosphere in a municipal scenario. There are a lot more people drinking the water, and that means a lot more treatment and treatment media that has associated emissions. But if we normalize to the number of users, then we come up approximately similar for residential and municipal water treatment. It's around 2 metric tons of CO2 equivalent emitted to the atmosphere per person per year. It's a little bit higher in the residential water treatment scenario than the municipal scenario. And that makes sense because you have some economies of scale when you go to a larger water treatment system. In our specific simulations, the savings, I guess you could say, really come from everybody sharing the same treatment vessel. So we can ship one treatment, activated carbon treatment vessel to one municipality rather than shipping individual vessels to each person's home and installing them there. So you get a little bit of efficiency by going to a larger water treatment system that goes to a lot of people. That 2 metric tons approximately of CO2 equivalent emitted to the atmosphere per person per year for the current drinking water standard can be compared to the annual emissions for just average American, and that's about 15 metric tons. So the 2 versus the 15 metric tons CO2 equivalent emitted to the atmosphere per person per year is more than a 10% increase in a user's emissions to the atmosphere. So we in our state, like those in many other states, have goals for decreasing our greenhouse gas emissions to the atmosphere over the coming years. In this simulation that we have run here, we're going the opposite direction. Our users are having emissions, significant increase to their emissions to the atmosphere so that they can have drinking water that meets the current standard for PFAS. For different drinking water standards or target levels, of course, we end up with lower emissions if we have a less stringent standard. And of course, if we have a more stringent standard, we have higher emissions. You need more activated carbon treatment media to get to those low standards, and so that means higher emissions. Things get especially extreme when you get to this low target water concentration of 0.002 micrograms per liter for PFAS. Then we're looking at somewhere in the ballpark of, on this graph, about 13 metric tons of CO2 emitted to the atmosphere per person per year to about 17 metric tons per person per year. That's basically the annual emissions for an American, 15 metric tons. So when we have our water treated to this more stringent standard, we can expect an approximate doubling of a person's emissions to the atmosphere over the course of a year, so that they can have water that's treated to this level, at least in our simulations. So that is a lot of emissions to the atmosphere. That's for coal source activated carbon. For biomass source activated carbon, things do fare better. You can see that we have smaller y-axes on all of these cases when you look at the coal source activated carbon. And if you look at our interim drinking water standard, that 0.02 microgram per liter standard, we're at about 1 metric ton of CO2 equivalent per person per year for both of these scenarios. So it is a lower emissions, and so we can have decreased emissions by going to a biomass sourced activated carbon. But still, a metric ton of CO2 equivalent per person per year is a lot of emissions to the atmosphere. So if we do want to have drinking water that meets that interim standard, then it will mean significant increase to a user's emissions based on our estimates. So this work led us to also think about risk reduction as well. So we made this little graph so that we can have some context, because that's really what people are thinking about when they're looking at treating PFAS and removing it from drinking water. They're trying to achieve risk reduction. So this graph here is one where we have PFAS concentration on the y-axis, and you can see it's on a logarithmic scale, and it's a huge range. You can see many orders of magnitude variation here. We also have the 2022 EPA health advisory levels for PFOA and PFOS. They're shown here. These are really low levels. Then we have the current approximate laboratory reporting level for these two PFAS constituents, which aligns with the draft EPA MCLs for PFOA and PFOS. The little blue dots on this graph are the target water concentrations that we did in our study. So we have the current main interim standard, and then those less stringent standards and those more stringent standards. So you can see it's really those more stringent standards, even more stringent than what our current main standard is, that gets us in the ballpark of what the reporting levels are for PFAS and the draft EPA MCLs for PFOA and PFOS. The EPA health advisory levels are, by the EPA toxicologist estimation, any value above that imparts some risk to some receptors that are drinking that water. So that would mean all of these concentrations that are here as target levels, including the proposed EPA MCLs for PFOA and PFOS. We in our community, I know in my even local community, we are talking a lot about we want safe drinking water for our population, and that's probably going on in a lot of different places. A more accurate way to say that may be that we want more or less risk reduction and more or less greenhouse gas emissions to achieve that desired risk reduction. And so this work that we did led us to think that there are several policy directions that folks may go, and we just put two main bullets here for folks to be thinking about. This is really for regulators to be thinking about. One is that we would suggest that where possible, that greenhouse gas emissions be considered as one cost in a cost-benefit analysis for a drinking water standard. So it's not to say that greenhouse gas emissions would be the most important cost, or that they would be weighed the same as any particular desired level of risk reduction. But if those emissions can be considered as one cost, then the broader environmental footprint for treatment of PFAS could also be considered. So that's one idea that we had for a direction that policymakers might go, is to consider those greenhouse gas emissions. Another sort of like sub-direction is, that's like a subcategory of that, is that don't just do that. Let's not just do that in a in closed door setting. Let's make it said out loud and even written down, so that it is an explicit statement that greenhouse gas emissions for the current drinking water standards and future drinking water standards would be considered. And the reason I'm saying, hey, let's make sure we say this out loud a lot, if you want to go that direction as a regulator, is that right now, technology developers, when they're reporting the level of treatment for their specific approach for sweeping out PFAS from drinking water, they really focus on the level of treatment achieved, and they may tell you a little bit about the potential cost. It is not as often or frequent that a technology developer will report the level of greenhouse gas emissions associated with their treatment technology. And for those of us that are interested in that and think that it matters, it would be really helpful if it was understood that regulators are considering it, and that way those technology developers would feel compelled to report it. And then we could help it be part of our hopefully systematic evaluations of this topic. So here are some references that you can look at, and this is a webinar that's being recorded, so at some point you can pause if you want to take a look at these. This work that I presented is pulled from a write-up that we did in Maine Policy Review. It's this last reference down here, so you can look at it in more detail and look at the methods. And so that concludes our first talk about a very narrow, immediate PFAS remediation topic. We are now going to hear from Paige to tell us more broadly about PFAS treatment technologies and greenhouse gas emissions.
All right, thank you, Ben. Let me try to share my screen. Can you see that okay? Is anything showing yet?
Yes.
Yes, awesome. Thank you for the confirmation there. All right, so as Ben mentioned, I'm going to kind of expand the view of the conversation he just presented, but I first want to acknowledge the work he published. The publication he mentioned right there at the end is the inspiration for the evaluation that we did at Jacobs. So I'll kind of refer back to that as I talk through. But today, again, we're going to talk about what is the environmental footprint of PFAS treatment technologies for both liquids, and also some discussion of solids. A quick agenda for today. First, going to go over the why of the presentation. Why is it important to evaluate and consider the environmental footprint of these PFAS treatment technologies? Then we'll talk through the methodologies we used during our evaluation, including the development of scenarios, the gathering of data, and the calculation of the footprint. We will, of course, go over the results of the evaluation and then wrap things up with some conclusions and opportunities. So for this presentation, we will start with how will we remediate PFAS? So due to the nature of PFAS and its differences from some of the more traditional contaminants, we really have to ask how will we truly remediate PFAS? PFAS have obviously been attracting more and more attention as emerging environmental contaminants, increasing the pressure on industry to be innovative in their treatment technologies. Currently, as we just learned, many of the more tried and true remedial technologies are not quite as effective with PFAS. The few traditional methods that are effective do not completely remove PFAS from the environment, and in some cases, they cannot sufficiently meet those low concentrations we're considering for our screening levels, which brings up another point. What standard will we remediate to? We just saw the importance of that. As we might already be very aware, the standards for cleanup are a moving target. However, the likely pretty low cleanup levels coming for PFAS will potentially require really long-term and extensive treatment operations. This will make the environmental footprint even more significant. So the goal of this evaluation, again, was to build off of Ben's great work to help us better understand the magnitude of the environmental impacts of a wider range of technologies being used for PFAS treatment, and to also consider some opportunities for future savings to reduce that impact. So now on to our methodology. For this evaluation, we wanted to establish a standardized approach to more fairly evaluate the different technologies currently being utilized. So for this, we developed some hypothetical scenarios, nothing from an actual project, just hypothetical scenarios. We established general assumptions, we gathered the data, and then conducted the environmental footprint calculation. So let's step through each of these in a little bit more detail. The scenarios we considered for this evaluation were designed to mimic a range of situations we may encounter in our environmental remediation projects. Again, not based on actual project information. Additionally, to simplify, we have focused in on just two of the key target compounds, so PFOA and PFOS. Let's talk a bit about each of these scenarios shown here. So the first scenario, liquid scenario 1, this one considers 1,000 gallons of liquid with a starting concentration of 50,000 nanograms per liter combined PFOA and PFOS. This could represent things like the high concentration, low volume sources we encounter on projects, things like monitoring well IBW, some thermal treatment condensate, soil washing waste streams, etc. The second scenario, liquid scenario 2, considers 50 million gallons of liquid with a starting concentration of only 500 nanograms per liter combined PFOA and PFOS. This could represent things like low concentration, high volume sources, potential pump and treat, groundwater, hydraulic containment systems, maybe contaminated site dewatering systems, etc. The third scenario, solid scenario 1, switching media here, considers 5 55-gallon drums with a starting concentration of 10,000 micrograms per kilogram. This could represent the low volume scenarios we encounter projects, again, potential IDW, maybe some drill cuttings from our environmental investigations. And the fourth and final scenario, solid scenario 2, considers 10,000 cubic yards with a starting concentration of 10,000 micrograms per kilogram. This again could represent the high volume scenarios, things like potential source area contamination. Once we had established these standardized scenarios, we defined some general assumptions to kind of level the playing field between each technology type. Some examples of the assumptions we provided are, we provided a standard set of GenChem parameters or soil parameters. We assumed all of our hypothetical site is located within the US, and the same hypothetical location was used for all scenarios, and that all vendors were an equal distance away from the site. With that brings us to the data gathering phase of our evaluation. So as we kind of mentioned at the beginning of this presentation, there are developing technologies that are being considered for PFAS treatment. We wanted to work directly with the vendors developing and implementing those PFAS treatment methods, so we'd have the most up-to-date understanding of each of those technologies. So industry-leading PFAS treatment technology vendors were contacted and presented with these 4 hypothetical scenarios. We asked for each to provide general treatment operational information to derive the environmental footprint values. We reached out to about 40 different treatment vendors. We received enough input from about 13 to 15 of them, with some helpful insights provided by a few other vendors. What we're presenting here on the slide are the treatment technologies actually included in the evaluation. So just note that this is not a comprehensive list of all of the PFAS treatment technologies that are currently available. Some additional technologies obviously exist. However, we, for our evaluation, may have just not received adequate information from those vendors. Now on to the environmental footprint. So although an environmental footprint analysis may consider many other components, this evaluation considered only the factors that have the highest potential to contribute to our environmental footprint. This includes things like treatment material production and transportation, equipment use, electricity use, and material disposal. Each of the vendors, again, were contacted and provided a standard set of questions related to those scenarios, focusing in on the information related to these factors. The components are obviously not universally applicable to all treatment technology types, but this was used as a baseline for initial evaluation. The vendor inputs were then summarized, converted to standardized comparable values, and then we entered them into Sitewise. If you don't know already, Sitewise is a tool that is designed to help calculate the environmental footprint of remedial alternatives. The tool you can download from the SURF website. It comprises a series of Excel sheets and provides detailed assessment of quantifiable sustainability metrics. So there's a standard set of inputs you are able to utilize within Sitewise. A few examples shown here. Many of the items we use as inputs in this tool are items that you might compile already for a cost estimate, things like materials or drilling methods and counts, residual handling, things like that. So we standardized our inputs from all of those vendors to align with the categories within Sitewise. Once we entered all the inputs, the standard assumptions within Sitewise were utilized for the evaluation, and we were presented with the outputs from Sitewise. So this is an example here, just an example from Sitewise. You can see here that it covers a large range of parameters, things like greenhouse gas, electricity, energy, water, and so on. However, for this evaluation, we're going to look just at greenhouse gas emissions for simplification. Now, time to take a look at our results. Let's start with liquid scenario 1. So remember, this is the low volume, high concentration scenario. We received enough input from the vendors to evaluate 5 treatment technology types. We have supercritical water oxidation, ion exchange, electrochemical oxidation, foam fractionation, and granular activated carbon, along with regenerated gas. Each of the results presents a range from the different vendors within each treatment type category. So the error bars represent that range there. For comparison, we've included here the approximate emissions from driving about 5,000 miles to kind of get an idea of the magnitude of these emissions. I don't know about all of you, but sometimes metric tons of greenhouse gas emissions isn't something I immediately fully understand the magnitude of. So overall, the footprints of these treatment technologies are relatively similar to one another. They are pretty comparable magnitudes. We've also considered which components contribute to these footprints, shown in the pie charts at the bottom. So at such a small scale, 2 of the largest contributors to each of these technologies are the transportation of equipment and material to the site, and then the use of equipment and electricity. So let's look at 2 of these technologies in a little more detail. So first, electrochemical oxidation indicates the highest overall footprint, with the main contribution from equipment and electricity use. So there may be an opportunity in the future for reduction as electricity sources can be adjusted. Next, let's look at foam fractionation here. It's the smallest footprint of this technology. It's nearly all coming from just moving the equipment to the site. So overall, it's important to note the overarching differences in these technologies. Some are destructive and others are not. So this distinction in end product should be noted because the destructive technologies completely remove PFAS from the environment, whereas others produce a reduced amount of waste that must then be managed at a landfill. So an important long-term consideration. Next, let's take a look at the results for the second liquid scenario, high volume, lower concentration. We received enough input to, again, evaluate 5 treatment technology types. Please note, though, that these results now are presented on a log scale, so indicating we have a much wider range of magnitudes than we did with the first smaller scenario. Additionally, we've added in a comparison of electricity used of a home over 1 year, so at 2,000 homes, electricity use, so a much larger magnitude. We again compared the breakdown of the components contributing to these footprints, which look a little bit different than the previous scenario. So this scenario consistently has highest contributions from either the production of treatment materials or the equipment and electricity use. So when we're scaling up our process, we're seeing contributions from different components. So let's look at a few of these technologies in a little more detail again. So first here we have supercritical water oxidation, ion exchange, and GAC. They all have relatively similar breakdowns with contributions from both treatment material production and equipment electricity use. On the other hand, though, we have electrochemical oxidation and foam fractionation, which each have their entire contribution from one single component, indicating we may have some opportunities in the future to reduce the impacts there. The next scenario, solid scenario 1, switching media. This is the low volume scenario. We evaluated 2 treatment technologies, thermal desorption and then soil stabilization, along with excavation to a landfill. We all know excavation is not an innovative technology, but it is a commonly used alternative for removal of the contamination from the site. For landfills, we have also added in a scenario in which backfill is required for the source area. This is generally expected, so we've presented both options here. For thermal desorption, many of the vendors we talked to indicated that they are already using solar power as an option for their treatment processes. So we've added in a category in which nothing else is altered besides the use of solar power instead of just the US average breakdown for electricity. So overall, the smaller scale scenarios have similar magnitudes of the greenhouse gas emission footprints. They're all under 2 metric tons. We've again added in some mileage for comparison to have a better understanding of what those metrics indicate. And again, we have the breakdowns for the contributing components. They're a little bit more variable for this scenario. So we have the landfill option. This, of course, indicates that material disposal is a significant contributor as expected, while soil stabilization and thermal desorption have contributions from treatment materials and equipment electricity use, among others. The final scenario, solid scenario 2, is the high volume scenario. So we evaluated 3 treatment technology types for this scenario. We had thermal desorption, soil stabilization, and this time soil washing, along with, again, excavation to a landfill. Again, we show the comparison for greenhouse gas emissions for electricity at homes for reference. We show the same option for landfill with one including backfill. And again, different options for the thermal desorption methodology. So some of the variables within thermal desorption vendors were the use of solar panels, again, but also each vendor utilized a different method to manage their condensate. So we have 2 different scenarios again shown for this one. One where condensate is taken to a landfill and disposed of, and a second with the condensate treated on site using something like GAC. So overall, the magnitudes are more similar for this scenario than the larger liquid scenario, so no log scale for this one. Here we can see the components that contribute to the overall footprint. Landfill has a high contribution for material disposal, of course. Thermal desorption options are relatively similar to one another. However, treating the condensate on site leads to a higher footprint, but more greatly reduces the amount of PFAS waste we're disposing of. So a trade-off there. So at this time in our evaluation, we have a few considerations and some potential opportunities for PFAS treatment technologies moving forward. First, the long-term resiliency of treatment technologies. So technologies resulting in disposal at landfills are, of course, accomplishing risk mitigation. However, they do not remove PFAS completely from the environment. So when we're utilizing one of those types of technologies, we may consider the addition of a destructive technology to minimize waste disposal requirements, which may be costly and have a higher impact on your footprint, but would prevent potential re-entry of PFAS into the environment. Next, the main contributors in a lot of these larger scale scenarios were electricity usage and transportation. So with these having a larger impact, there is an opportunity to try and design out some of those contributions. Things like considering implementation of solar panels, maybe utilizing power companies that have higher percentages of renewables. A side note, this presentation was shared in Europe, where it was noted that some of the electricity-heavy technologies would have a much lower greenhouse gas emission associated, as some of their electricity profiles utilize more renewable sources. Additionally, this impact may be reduced in the future with the use of electric vehicles. Next, in this evaluation, we did not request the combination of any treatment technologies. However, the concept of treatment trains may absolutely be considered in the future where applicable. The addition of a different technology at a pre or post-treatment step could create efficiencies overall and reduce the overall treatment footprint of some of the technologies. Finally, this evaluation focused only on greenhouse gas emissions. There are many other important sustainability metrics that should be considered when looking at implementing one of these technologies at your site. Things like biodiversity or social impact, water use, resiliency of the treatment technology, etc. However, again, the goal of this presentation was just to wrap our heads around the potentially significant impact PFAS treatment will have on our environment. So again, with the low levels expected for remediation standards, the long-term operation timelines, it's important for us to really consider the potential impact we might be having on the environment and look for opportunities for future reductions. So with that, I'd like to say a big thank you to all of my co-authors and all of the vendors that contributed to this evaluation. We will have this coming out as a publication very soon, so I'm sure we can share that shortly. And thanks again, and I think now we have some time for questions.
Yeah, thank you, Paige. Thank you, Ben. We have had a few come in so far. Just a reminder to the audience, you can go ahead and drop those questions in the question bar, and we'll get to those. First question so far, wondering if you've had any response from regulators on these considerations yet, and if so, what their response was.
I can speak a little to that. This work was presented, this is very Maine specific, as you can see, the work that I did. So we presented it at the Maine, I think it's called the Sustainability in Water Conference, something like that, in the spring of this year. And that's a great conference if you live in Maine, and regulators do attend it, and there was a PFAS session. The Maine state toxicologists and a couple of other toxicologists were in the PFAS session. They gave great presentations about some work that's being done on PFAS uptake in plants for agricultural scenarios. So they had to sit and listen to my talk too, unless they wanted to do something else. So they did sit and listen. And I spoke to, one of them spoke during the session and just said, thank you very much for doing this work. Said that it was important work. Another one talked to me afterwards, basically because I chased him down. It was like, hey, how are you doing? And he said that it was good work. He was very appreciative. But as far as like a dialogue about where is this really, this line of thinking of importance to them, not sure about that. But I do think that it's at least on some folks' radar, and that's good. And I mean, the people that actually have to settle on a drinking water standard or any sort of cleanup standard have one of the hardest jobs you can imagine. The judgment that they have, the good judgment that they have to think about protecting people and then the environment more broadly. I'm not sure, they probably have a lot of things on their mind. I don't know how muddled it is. It's quite muddled in my mind, but we've gotten positive, but not necessarily decisive responses from regulators so far.
Great, thanks, Ben. Another question coming in. Would you, and I think this is a little bit directed to Paige, but obviously both of you tackle this. Would you expect the results from SiteWise to be significantly different if you were considering another class of contaminants but the same treatment assumptions?
So just treating for a different type of contaminant. Yeah, I think the main factor is the operation timeline. So that is considered in the site-wise assumptions. So things like electricity use, I think, would still be a much higher output for PFAS because we're operating for a much longer amount of time. Also, things like materials used for treating PFAS are increased. I think just as Ben shared for GAC alone, you have to use a much larger volume when treating PFAS than when we're treating some of our standard remediation contaminants. So I think a lot of the inputs would be similar categories, but would be of much larger magnitudes, which would have an impact on the site-wise output, also increasing the outputs of the greenhouse gas emissions. So I don't know what kind of comparison it would be. It might be interesting to look at what's been traditionally done at those treatment technology types, and then also comparing that to PFAS. So it could be something to look into. But yeah, I would expect an increase.
Yeah, maybe similar along those lines. Ben, when you guys were looking at the greenhouse gas emissions for granular activated carbon, did you look at any scenarios where granular activated carbon was already being used as part of the drinking water treatment train, and what that change might be due to targeting PFAS specifically?
We were certainly informed by what is being done out there. We tried to use data for sites that have PFAS affected water, and one municipality where they are using activated carbon for cleanup. Also talked to one of my coworkers that's one of the co-authors, Mitch. He does install these sorts of systems, so just made sure we did some ground truthing. But I think what really that question is getting at is something that is quite site specific and is going to end up having to be like an estimate for each site, is that the mix of your water when it's really the case for many treatment approaches, but especially for activated carbon, the mix of your raw water really affects what kind of treatment you can truly achieve. And so the research that we pulled to get our adsorption parameters was actually for water from a surface water source down in North Carolina, down in the Chapel Hill area. And to get that even remotely similar to what we would expect for groundwater, we had to use their raw water treatment, pre-treated data before we'd start plugging it into our calculations. So there probably in some cases will be pre-treatment of your water just before you ever put activated carbon in line, so that you aren't wasting a bunch of your activated carbon on non-target compounds. Like I said, that's probably going to be very site specific. And one hope would be that as we bring more and more sites online for treatment, that we can do some sharing. Doesn't have to be in an academic setting. Maybe state regulators want to set up a little sharing website where we can see, hey, what's your water look like? What are your adsorption parameters looking like? How do you tune it? If we can get that sort of information, it's really going to help us optimize our efficiency while we're using activated carbon as a treatment approach.
Thanks, Ben. Yeah, question for Paige. When reaching out to vendors, had any already looked at this or similar matrices for their respective technologies?
Yeah, that's a really good question. So some of the vendors immediately had information to provide. I will say, I think if everybody on the phone knows, Australia's done a lot of work already in PFAS, the PFAS treatment world. So the vendors I worked with in Australia had numbers ready to hand over almost immediately. They just kind of curated those responses to our hypothetical scenarios. So I think in Australia, those vendors already include, kind of as Ben mentioned, this sustainability evaluation, something to consider when they're proposing their treatment technology types and selling these technologies. I would say it was a new concept for other vendors, but they were all very willing to work with us on it, especially when you break down the types of inputs we include in this evaluation. Like I said earlier, it's kind of what you would include in a cost estimate. So it's not reinventing the wheel every time. If you want to look at your greenhouse gas emissions, using SiteWise is a great place to start, and you probably already have some of those metrics considered. But I would say it was kind of a mix of the vendors that were already looking into this and some that were not. And I will say too, just for general knowledge, the vendor inputs were not allowed to share with what people provided, as a lot of these technologies are proprietary, and vendors are still working on developing those technologies.
Thanks. Question here, is it possible to compare the incremental risk of additional greenhouse gas emissions to the risk of incremental PFAS concentrations to better understand the balance of the two?
Go ahead, Ben.
When people, my understanding is that when people especially go with a very standardized life cycle analysis, that's really oftentimes the type of thing that they're doing, is they're trying to somehow create a comparison, an apples to apples comparison between different environmental impacts. So theoretically, I think it would be possible to do that, and how much you believe your output would be a function of your belief in the methodology, and especially, like, I think when you get there, especially for, well, actually, unfortunately, I'm thinking out loud on this, the risk from PFAS is not well understood. The risk from climate change has huge ranges of uncertainty. So I think you could go there. It could possibly be informative, but I also suspect, thinking out loud, that you're gonna have some big error bars, and I'm not sure if you would come up with something that would feel very meaningful. And then of course you will never in such an analysis be able to match the importance of people in your own life and your local community to that with the global community. And that's the problem with climate change, is that, or a problem with climate change, is that it is a very global problem that has to be solved by a lot of people doing a lot of actions for everybody, but the risk is shared very broadly and diffusely.
Yeah, thanks, Ben. I figured that'd be a little bit of a challenging question, but definitely something that needs to be thought about. Yeah, when you were looking at the greenhouse gas emissions, did you consider other, and I'm not sure this term, WOLC tools, and did you update the SiteWise lookup table to include specific factors?
I think that one's for me. Yeah, so some of the
Whole life carbon, thank you.
Thank you, yeah. Some of the SiteWise assumptions are a bit outdated, so we did update the specific factors that are used through the SiteWise tool. So we pulled those from different resources. I also haven't heard of that acronym, so I'm going to look at that. But yeah, we did pull in more updated information for some of those general assumptions that are in SiteWise. So yes.
Yeah, I'll add to that just so that users are aware, SiteWise, in some ways, in many ways, it gives you direct input parameters you can use, but it's also just a framework. And that's largely what Paige was using it for, is just a consistent framework for your analysis. She was probably plugging in a zillion user-defined inputs, and SiteWise makes that possible. It's a great tool.
Definitely. Thanks, Ben.
Ben, did you use SiteWise or CEFA as part of your calculation?
Of course, I'm a member of SERV. I use yeah, anywhere I could, I use SiteWise. And if I had really understood the flexibility of SiteWise, I would have used it more. I should say we would have used it more, I and my co-authors. I moved away from it early on because they have one input parameter for the embodied emissions for activated carbon, and it was 1, and like I kept trying to chase the reference value for it and never really got there. So I ended up going my own route to get that from other people's LCAs, and that kind of moved me away from Sitewise. But if I just would have realized, hey, I can just change that and change a couple other things in Sitewise, I could have just stuck with it a lot more. But things like driving your vehicles to and from Pennsylvania, Sitewise. Things like steel manufacturing for a treatment vessel, Sitewise. So it's a great tool for a lot of things.
Yeah, and I just wanted to remind the audience here, I did drop a note to everybody in the chat of a link to the initiatives page on the SURF website. There are links to both Sitewise and SEFA on the website, and as well as SURF, Sitewise and SEFA training videos to kind of help get your feet wet and get going along those processes. I think the last question I have at this point, Ben, when you were comparing greenhouse gas emissions between coal and biomass sourced carbon, did you see a reduction in the greenhouse gas emission from primarily from one specific step in that carbon life cycle process, or was it more kind of shared across multiple steps when looking at the two different carbon GAC sources?
For me, those two input parameters, you saw an 18 kilograms CO2 equivalent per kilogram of activated carbon versus 9. For me, those are largely black boxes. The article that I got those data from, I believe, are listed in the references of this slide presentation. But even if you don't see them there, you could see them in the article that we wrote. And you'd have to do some chasing to be able to answer that question. I felt like it was a good solid estimate at the time that I was reading it, but as far as like, why is it so different between the two, I'm not sure.
Yeah, thanks. Well, I guess if you guys don't have any additional last closing thoughts, additions here, I'll turn it back over to Gerlinde to give us a quick update on a few things with SURF, and we'll be wrapped up.
Good discussion there at the end. Thank you again to both of our presenters. As we wrap up this year at SURF, I do have a few announcements to make. The Board of Trustees has 3 positions opening up for 2024 elections. The open positions will be the treasurer and 2 member at-large positions. Nominations are currently open through January 12th. So if you or anyone you know are interested in becoming more actively involved in SURF, please consider nominating them or yourself for the board, and you can do that by reaching out to Kathy Adams at sustainableremediation.org. As always, we're looking ahead to what's next. We're planning our webinars for 2024. If you have a topic that you would like to present on or an idea of something that you would like to see featured, please reach out to Chris and we can get you or your idea on the agenda. Finally, as we mentioned, a recording of this webinar and our past webinars are also available on the SURF YouTube channel and SURF website. There you will also find some training videos and tools for the resources used in this presentation, Sitewise as well as SEFA. There's a link to that in the chat here as well, like Chris mentioned. SURF has our next in-person meeting in mid-March at the AEHS West Coast meeting in San Diego. We'd love to see you there. Registration is already open, so head over to the AEHS Foundation website for more info and to sign up. Finally, thank you so much to our SURF sponsors listed here. who support us and allow us to be able to continue to advance the practice of sustainable remediation in so many ways. We're really grateful to all of our sponsors. I think that's about it. Everyone, happy holidays and have a nice time off and Happy New Year, and we'll see you in 2024. Bye.